Prandtl's bell-shaped lift distribution has been a topic of much interest recently, and is kind of a hotly debated topic about what it really means and what the benefits are of this particular lift distribution as opposed to the elliptic lift distribution, which has long been understood as the optimum distribution that minimizes induced drag. So let's dig into this and better understand the principles behind this bell-shaped lift distribution, what it means, and maybe also what it doesn't mean. Okay, so in order to do this, we do need to dig into lifting line theory just a little bit. Okay, I'm just going to touch on the math here to lay a groundwork from which we can extract some things. But you don't have to understand all of this math to understand the concepts of what we get out of this. Okay, so I'm going to start by writing a non-dimensional lift distribution, which is a little bit non-conventional, but one way to non-dimensionalize a lift distribution. Now, L tilde here is the local section lift. B is wingspan. Theta is a location along the wing. Okay, and I'll just put over here real quick how theta is related to your span-wise location. We're going to use Z for the span-wise location, and to get that from theta, it's equal to minus B over 2 times the cosine of theta. Okay, so this is, maybe I'll take off those parentheses. So, yeah, so this is just cosine clustering, basically, but it's a way to get into the Fourier sine series that are often used in lifting line theory. So anyway, if we know the lift, back over here on the left, if we know the lift at each theta location or Z location and multiply it by the wingspan and divide by the global lift, that's what capital L without the tilde is, that's the global lift that's being generated. This is one way to non-dimensionalize a lift distribution across the wing, okay? So from lifting line theory, you can write this as an infinite series, and it looks like this. We have 4 over pi times the sine of theta plus an infinite series, so we're going to sum from n equals 2 up to infinity of, we're going to call it b sub n. B sub n are just our Fourier coefficients times the sine of n theta. Okay, so this is just an infinite series definition of some lift distribution. With that as our base, we can now compute the induced drag. So the induced drag, a dimensional induced drag, can be written like this. So I'm just going to write it down and then we'll walk through it here. We got W over B squared divided by pi times rho, which is the density, V infinity squared is the velocity, times 1 plus the summation from n equals 2 up to infinity of n times b sub n squared. Okay, so this is an equation for induced drag. Let's just walk through it here for just a minute so we understand what the components are here. So one thing that we've swapped out here is the lift for weight. Okay, so we're going to assume steady level flight, and that's generally what we're talking about when we're talking about really efficient lift distribution. So we're saying that the weight, or excuse me, the lift has to be equal to the weight. So this global lift up here is equal to the weight. Okay, so I'm just going to put that in there. And so really you could put in lift right there for that W, but it's easier to think about it in terms of weight for what we're going to understand next here. So okay, so we've got the weight divided by the wingspan squared divided by pi, rho is the density, V is the velocity. And then it depends, of course, on all of these Fourier coefficients over here, what your induced drag is going to be. And this equation just comes directly from lifting line theory. If we can define a lift distribution like this, we know how the induced drag is related to the this Fourier sine series here. And in fact, it's this that you can, from lifting line theory, you can show that this is the induced drag if you know what each of these Fourier coefficients are. Okay, so let's first start with the elliptic lift distribution. The elliptic lift distribution is really well understood. Basically, if you look at this equation, you say, well, I want to minimize induced drag, And I can do that by changing the lift distribution. Well, we change the lift distribution by changing these Fourier coefficients. So if I could choose the value for each of these Fourier coefficients in order to minimize the drag over here, it's quite obvious that for the elliptic, to minimize that equation, to minimize the induced drag, what we'd want to do is we want all of the Bn values to be 0, right? Because they get squared. It's Bn squared right there. So we don't want negative values in there. Negative values are just as bad as positive values, and so all those values are going to get squared. So we want all of those to be 0, and that would minimize induced drag. So what we have kind of tacitly assumed in that is that the weight here is independent of my lift distribution. Okay, so and that's usually how we start looking at the problem. At first we say, okay, I've got a given weight of an aircraft and a given wingspan. Well, how do I a given weight of the aircraft, or the weight that the lift has to be equal to, and a wingspan, how do I minimize induced drag? Well, I set all these terms equal to 0, and that's where we get the elliptic lift distribution. Okay, that results in the elliptic lift distribution. In fact, if you come back up here and set all of these Bn values to 0, you're left with this 4 over pi times sine theta. This is the elliptic lift distribution in this non-dimensional form here. Okay, but that's not the only way to look at this problem, and that's what Prandtl, actually he published his first paper on this alternate view of looking at this in 1933. Okay, so I'm just going to say here Prandtl 1933. And by the way, he had published lifting line theory about a decade before that, a little bit more than a decade before that. And in those original publications, he had already talked a lot about the elliptic lift distribution. But so this is about 10 years later, he comes out with a new publication. He says, hey, there's another way to look at this. Okay, and by the way, this publication was all in German. Of course, all of his or most of his publications at the time were in German, but unfortunately, it was never officially translated. A lot of his other work was translated into English, and unfortunately this particular publication was never officially translated and published in English until recently. My advisor Warren Phillips and I went through, carefully translated it, and published this in an AIAA conference, and you can look that up and get a copy of it. But anyway, so there's now an English translation of it, but I think that's kind of caused some of the confusion, is that we haven't had a really good English translation to look at that's in the open literature for people to study. So anyway, we were hoping to help with that issue a little bit with that translation. Okay, so let's look at what he did in that paper. So instead of with this elliptic, let's just mention over here, we made some assumptions. We assume a set weight and wingspan. Okay. Now let's back up for just a minute. What if we hadn't assumed a set wingspan, right? Let's start there. So if we look at this equation, this is our fundamental equation of induced drag. We're trying to minimize induced drag. Well, what can we do to minimize induced drag? Well, it's very obvious that wingspan here is in the denominator, and it's squared, right? So we've got a b squared here in the denominator. Well, of course, increasing the wingspan is going to have a very significant effect on decreasing our induced drag. Well, but when we talk about the elliptic lift distribution, but even for any wingspan still, by setting these terms 0, we're going to get back to the elliptic lift distribution, be able to minimize the induced drag at that particular wingspan. But what we don't often talk about is this weight term right here, which we said was equal to, well, it's really the lift term out of lifting line theory, but we're saying that it's got to be equal to the weight of the aircraft that we got to carry here. Okay, so another way to lower the induced drag would obviously be to lower the weight of the aircraft, right? If we could reduce the weight of the aircraft, that would reduce the induced drag. But again, for a set weight and wingspan, the way to minimize this equation, once W and B are set, is to set these terms to 0 here, these Bn terms to 0, and that gives us the elliptic, okay? So let's first look at the logic behind Prandtl's alternate way of looking at this. And basically the logic boils down to the fact that the weight of the wing depends on the lift distribution over here and the wingspan, okay? So we can't really set, in general, these are all related. You know, there's a certain wingspan that's associated with this weight and a lift distribution. And let's just talk about why that is here for a second. So if we were to look at, on the x-axis here is our wingspan coordinate. Again, we're using z for that. And then on the y-axis here, if we were to put a lift distribution on here, from the root, which is 0, out to the tip here. So we've got some lift distribution. Well, the wing spar has to be strong enough to be able to offset that, to be able to withstand the bending moment created by that lift distribution. Okay, so first white here is the lift distribution, and then let's just kind of draw a notional wing bending moment. So the bending moment out of the tip is 0. As you get closer to the root, it increases, and it depends, this bending moment here depends on what this lift distribution looks like. So we're going to call this bending moment. Okay, so there's a relationship here, and so and then the bending moment, whatever it has to support there, that bending moment then translates to the size of spar that is needed. So this information gets used to size the spar. So we size the spar off of that, and then the size of the spar then factors back into the weight of the aircraft up here, okay? So as we increase the wingspan, then if we kept the same lift distribution and we just increase the wingspan, well, the bending moment would go up, the spar would get larger, and so W would also get larger. So we can't just increase B without changing the weight of the aircraft. They're linked together. In the same way, we can't just change the lift distribution and go to a completely different lift distribution without that affecting this bending moment and therefore also the weight of the aircraft. So these three parameters here, the weight, the wingspan, and the lift distribution, are all intertwined. They're linked together. So originally, with the elliptic lift distribution, we kind of decoupled the problem. We said, okay, we're just going to assume we know the weight of the aircraft. We already know the wingspan. Those are fixed. Then what's the lift distribution that minimizes induced drag? And so that's where we set these values and we come up with the elliptic lift distribution. But Prandtl took a new view of this and said, let's look at the case where these are coupled. And he took a first stab at doing that. Now, it's actually a very challenging problem to look at this in general because it's actually quite a complex relationship between the lift distribution and the weight and the wingspan of the weight, because it goes through structures, right? This is now aerostructural coupling, where we're talking about how the aerodynamics affect the structures, the spar, and the structures can be a very complex problem. And so it's hard to solve this analytically, and of course Prandtl was solving this in 1933 without a computer. So his first crack at this was to simplify the problem a little bit and look at a simple case. Okay, so let's talk about what Prandtl assumed for his first crack at this. Okay, so let's write down his assumptions. And so he actually fixed the weight. So he held W constant. All right. So this W right here, he held that constant. But then he allowed the span to vary. Okay. So vary B, which is a span. And then he said that we need to fix the moment of inertia of lift. Okay, so let's talk about what that is for just a second. So if we were to put a center of lift out here, if we were to integrate this and basically put a center of lift out here where this lift could be balanced on the right wing, or as we have it drawn here, basically what he's saying is let's keep that moment of inertia of lifts, that's got some moment of inertia about this this origin here. So, some distance that the center of lift is acting multiplied by the amount of lift. So let's keep that distance times the amount of lift constant. Okay, so we're going to call that the fix the moment of inertia of lift. So fix moment of inertia of lift. Okay. Okay, so those were his assumptions, and he, as he worked through the math, he did a couple extra things that I'd like to mention here. One of those is that he assumed that the bending moment, if we come back to this drawing here, he assumed that the bending moment at any location was directly proportional to the size of the spar the weight of the spar that would be needed at that location. Now, he doesn't know what that proportionality constant is, and he never needs it, but he's just saying that that's proportional. Okay, so if we know the bending moment at any location, that's proportional to the weight of the spar at that location. Okay, so let's just write that down. Bending moment is proportional to weight of spar, and this is at each location along the span. Okay, so that's one thing. Now that proportionality coefficient, he assumes that is independent of spanwise location. Okay, so proportionality coefficient is independent of location. Okay, so why that is really important to understand is that that proportionality coefficient, basically, if you look at let's just draw a spar here. So we got a cross section of our wing, and let's use an I-beam spar here just to think about it for a second. So so basically, we're saying that any location we've got some bending moment that this section has to withstand, and so the bending moment is proportional to the weight of the spar, okay? And that proportionality constant is the same no matter where you are on this wing. Well, that's really only true if the thickness is the same at every location along the wing. Okay, so in order for that proportionality constant to stay the same, the thickness has to be the same. Now, he doesn't specifically say that, but because he's applying this assumption here that the proportionality coefficient is independent of location, that directly implies that the thickness has to be the same across the entire wing. So the thickness of a wing at any one location depends on two things. It depends on the chord of the airfoil at that location, as well as the percent thickness of that airfoil. Well, percent thicknesses usually only range between maybe 8 to 15%, so there's not a huge range or change in percent thickness. So if you're going to apply the same airfoil across the entire wing, what this all comes down to is that he basically assumed that the chord was constant. Okay, so really the analytic solution he comes up with here is really only true for wings with for rectangular wings, unless you're going to change the thickness of the wing or be able to keep the thickness of the wing the same even if you're changing the chord. Okay, so that's a really important thing over here. I'm just going to kind of star it, is that, and he doesn't specifically say this again, but he basically with his math is implying that the chord is constant or chord is independent of span location. So this is so basically we're assuming that this is only good for rectangular wings. Okay. Now a note on this, I actually have done some research on this particular question with one of my students, Jeff Taylor, and he looked into tapered wings and how much this solution changes actually with tapered wings. And it turns out it actually doesn't change very much, at least the particular questions that we were looking at. We didn't look exactly at Prandtl's problem here, and his same assumptions. But for the other things that we were looking at, it turned out that taper actually didn't affect the solution very much. So these analytic solutions that we're going to talk about here are actually fairly good, even for tapered wings, although in his math here, he's really constraining this to rectangular wings by not directly, but kind of indirectly by assuming this proportionality coefficient is independent of the location. Okay. All right. Now, one last thing that I want to point out here is that he also only looked at the bending moment. So the bending moment here as a function of span, he only included the effect of the lift distribution on that bending moment, okay? But in reality, we'd also have a weight distribution within the wing, and sometimes that's fairly significant. I mean, we have the weight of the spar in there as one thing, right? But a lot of wings actually carry fuel, or aircraft carry fuel in the wings, or they have engines sitting outboard here on the wing, or other fuel tanks or things like that. So anyway, he neglects all of that and says that the bending moment is a function only of the lift, okay? Not even of the spar weight itself, okay? So let's just write that down as one of these last things here, that the bending moment is a function only of the lift distribution. Okay, so we just want to, I'm just going to kind of box this. These are really important assumptions to understand when you're studying this bell-shaped lift distribution solution. You got to understand the assumptions that went into developing this. All right. So with all of those assumptions, Prandtl went through the math, and we could work through it here, but you're able to show that basically the optimum solution here is, if we scroll back up here, remember previously we had the optimum where Bn equals 0 for all n, but actually for Prandtl's 1933 solution, he gets that you want B3 equal to minus 1/3, okay? So that, and then all other B values, again, 0. So, and then, so I'll write that down here. Bn equals 0 for n not equal to 3, okay? So this is his solution. And so it's different, obviously, than Bn equals 0 for all n. And so you could plug this into this equation up here and figure out what the lift distribution is. And so if B3 equals minus 1/3 here, then what we get is 4 over pi times sine of theta minus 1/3 times the sine of 3 theta. Okay, so let's just write that down here as this other optimum lift distribution. So we call it the bell-shaped lift distribution. And the equation for that is let's see, so we've got B times L tilde of theta over capital L equals 4 over pi times the sine of theta minus 1/3 sine of 3 theta. Okay, let's just make sure that's right. Yeah, that looks correct to me. So this is the bell-shaped lift distribution, and what it looks like, of course, you're probably familiar with this, but basically it looks a little bit more bell-shaped. You get a distribution that looks more like that for a given global lift coefficient, rather than the traditional elliptic lift distribution, which would look something more like that for the same wingspan. Okay, so that's the lift distribution that he gets out of it. So let's just label these really quick. So this would be the elliptic, and the other would be the bell. What people have called, now I don't know that he ever called it the bell-shaped lift distribution, but it's a very common term for this lift distribution that he developed, the bell-shaped. Okay, so it's very important to understand that Prandtl never claimed that this is a global minimum to this problem. Again, I want to kind of box this problem. This is our fundamental equation that we're trying to minimize. And the key here is that all these things are related. The weight and the wingspan and the lift distribution are all related. But and he never claimed that he found a global minimum. All he claimed was that if you apply these assumptions here, then you get a different lift distribution that minimizes induced drag than the elliptic lift distribution. Okay, which was developed using a different set of assumptions. All right, so that's important to understand that Prandtl never made that claim in his paper. Okay, so let's just talk about some results of this lift distribution. So the bell-shaped lift distribution, let's see, results. Okay, so a couple results to be aware of is that the wingspan of the bell-shaped lift distribution, it increases relative to the elliptic lift distribution solution. It is a 22% increase in wingspan. Okay, so wingspan increases by, it's actually 22.5%. Okay, so this allows an increase in wingspan of 22.5% over the elliptic lift distribution. So basically, again, to come back and understand that, if we were to look at the if we were to take the elliptic lift distribution and compute basically the size of the spar that's needed to support that, and the center of lift out here, or the moment of inertia of lift, we can actually get the same size of spar, the same weight of the spar, and increase the wingspan by 22.5%. And apply this the bell-shaped lift distribution instead, and if we do that, what we get out of that is an induced drag. That induced drag is reduced by 11.1%. Okay, so these are the numbers that are thrown around out there, and they're correct. This is exactly what he came up with. So basically, let's actually redraw this figure here. That is would be a better comparison between the two. So let's start off with the elliptic lift distribution. So if our elliptic lift distribution looks something like this, so that's elliptic, and it has some center of lift multiplied by some moment of inertia of lift. So that's like the center of lift multiplied by the distance from the center line. Well, we can actually create a bell-shaped lift distribution on a wing that has let me try that one more time. That has a 22% increase in span, 22.5% increase in span, that requires the same weight of spar, basically, if you're only looking at the lift distribution effect on sizing that spar. Okay, so let's come back up here again and look at this equation again. So basically what we've done is we've increased the wingspan by 22%. And so now the B3 term here is minus 1/3. So that's going to increase the value over here, but our wingspan here is increased and the weight has stayed the same. So overall, actually the drag comes down by this 11.1%. Okay, so that's basically the fundamental portion or the fundamental development of Prandtl's bell-shaped lift distribution, and it's important to understand that the limitations basically of this development. Although it was really, it's really quite a groundbreaking way to look at this. Again, this is, to my knowledge, the first time somebody had looked at aerodynamics and structures together and tried to find an optimum solution for an aerostructural problem. You're looking at the two problems together, but it still has some significant. And there are other ways to look at this. There are other ways to put constraints on this problem, or different assumptions that can be made that actually result in different lift distributions than than the bell-shaped lift distribution. And so that's what we're going to talk about next. One more thing I'd like to point out before we move on is something that's not often mentioned with respect to the bell-shaped lift distribution, and that is that see, we've increased the span by 22.5%, and remember, we've basically kept the chord the same. Now, he doesn't explicitly state that again, but the math that he uses, it's very challenging to keep the thickness the same across the entire wing without keeping the chord the same across the entire wing. So anyway, so that's not completely true, but let's assume that it is for just a second, that the chord is constant across this. Okay, so again, we're talking about rectangular wings. So we'll have this original elliptic wing might look something like this, and then he kept the chord the same, that the proportionality constant between the bending moment and the weight of the spar, which means that chord had to stay the same, but increase the span by 22.5%. Okay, so this is this is our new wing here, and this, of course, is the center line of the wing. So we have this additional area that shows up. Okay, so our area actually has increased by 22%. So I'm going to say wing area increases by 22.5%. Okay, so why does that matter? Well, it matters because we've kept the weight the same. Our wing area increased, and so that means that the wing loading, which is the weight divided by the area of the wing, that's our wing loading. So our wing loading actually has reduced, because S is in the denominator, so and this is S here. So it's actually reduced by about 18.4%. Okay, so that reduces our wing loading by 18.4%. Okay, so why does that matter? Well, because the wing loading is related to our design speeds. So most of our design speeds, minimum power, minimum thrust, and even stall speed, are basically directly proportional to the square root of the wing loading. So this term shows up in our design speeds. Okay, so I'm just going to say that term, our design speeds are roughly proportional to that. Design speeds are proportional to the square root of W over S. Okay, so the wing loading, the square root of the wing loading. So that means that our design speeds have actually reduced by roughly, so these reduce by about 9.7%. Okay, so the reason that matters is because, see, we had our original wing here that was carrying the elliptic lift distribution, and usually we size that wing based off of the design speed. So we have a certain weight, a certain velocity that we need to travel at, and that basically sizes the area of that wing. Well, if we come back and now put on a bell-shaped lift distribution on that same airplane, and at least the way that Prandtl here is talking about, and just increase the wingspan by this 22.5%, well, that's going to change the wing loading. It's going to change the wing area, and it's going to reduce our design speeds by almost 10%. So that's just something to be aware of, is that the design speeds for these two different wings are actually different. If we just apply this bell-shaped lift distribution blindly, exactly how Prandtl kind of wrote about it here. Now, I have a great respect for Prandtl's work, and I'm not in any way trying to degrade what he did. In fact, I've learned a lot by studying his work and reworking through this math and understanding these concepts. And so I'm really appreciative of all of these ideas and concepts that he brought to the surface that are worth looking at. This relationship between aerodynamics and structures that can be looked at from a theoretical or an analytic perspective. And so in the next video, we're going to talk about another way to approach this problem that builds on the approach that Prandtl took here, but approaches it from a slightly different perspective, and there's some really interesting things we can learn from that method.